Our main subject today is going to be dislocations, but let me just start off by reminding you of the issue of defects in general. Defects in crystals do not mean the crystal is defective. What we mean by a defect in a crystal is a place where the perfect crystallographic order is somehow broken up. And in fact, these defects in crystals turn out to be very desirable because it is those defects that we use to control the engineering properties of materials. We classify the defects by their dimension. The zeroth order defects are point defects, such as solute atoms. There are then line defects, dislocations, which we'll talk about today, surface defects like external surfaces, which we'll talk about next time, and then volume defects, voids, and inclusions. Each of these levels of defects control a certain type of property of the material. The solutes are important for conductivity in semiconductors and strength in steel and such things. Dislocations control plastic deformation. That's their primary role. External surfaces control, for example, the shapes of crystals. And voids and inclusions are very important in the fracture of materials. So each level of defect has an important consequence for the behavior of materials. Intrinsic, well, point defects can come in two categories. We talked about this last time just by way of review. The first category are the intrinsic point defects. We can have a place where there should be an atom, but an atom is missing, and that's called a vacancy, a vacant site on the crystal lattice. These are the critical defects controlling diffusion through the crystal lattice in the solid state. We can also, but much more rarely, have defects in which an atom is driven into an interstitial site. This is a very rare kind of defect in ordinary crystals because it's very high energy. These kinds of defects do appear, and they can be important in certain kinds of crystals that have rather open structures. I think I mentioned the case of silver iodide or silver chloride, where silver ions can get into the wrong tetrahedral void, then they become very highly mobile, and that mobility is important in things like photography. But this is ordinarily an uncommon type of defect. Extrinsic point defects, well, again, they can be substitutional or interstitial. A substitutional defect is just a site at which the wrong kind of atom appears, whether that's a solute or an impurity, it just depends on whether we want it or not. The interstitial solutes sit in interstitial sites. These are ordinarily rather small atoms or ions that can fit in these rather tight spaces in the interstices. The most important and obvious property of the place where we see point defects is in the electrical properties of semiconductors. I mentioned this last time. If we take silicon, for example, which has 4 neighbors, 4 electrons, so the bonds are saturated. If we place the silicon by boron, we have too few valence electrons, so there is a hole in the valence shell. This hole is weakly bonded to the boron, can be shaken loose, or if you want, an electron can move in and occupy that position. Then the hole, which behaves as a positive conductor, can run through the lattice and conduct electricity. If we use a defect that has too many electrons, like phosphorus, we get an extra electron weakly bound to the phosphorus. It gets shaken loose and can conduct by means of electrons. So in semiconductors, we have the very important situation that by introducing the right kinds of substitutional atoms, we can not only increase the conductivity of the silicon by providing extra carriers, but we can control the type of the carrier, whether those carriers are holes or electrons. And as we shall see later, that's vital to the properties of microelectronic devices. In steel and other things, the interstitial atoms, particularly in body-centered cubic materials, can be very potent strengtheners. The reason is because of the asymmetry of the octahedral site in the body-centered cubic lattice where these atoms sit. They will try to make the site symmetric again. That will distort the crystal structure in the vicinity of the carbon and cause distortions and therefore strengthening. And this is a very important feature. That's what distinguishes iron and steel, the presence of these carbon atoms that add a great deal of strength. Line defects, dislocations, are a little bit more difficult to visualize. Let me start off by just showing you some. You've done a hardness test in the laboratory, haven't you? When you started out with hardness. The very first direct observation of a hardness test was done by Andy Miner here about 10 years ago when he was a graduate student. He's now a deputy director of the Center for Electron Microscopy up here. And what we did was to take a piece of aluminum and put it in an electron microscope, thin it down so that you could actually see through it with an electron beam, then take an indenter in the electron microscope and indent that piece of material. This was something that now is being done in many, many configurations for in situ studies of plastic deformation. Isotron produces a number of commercial devices that are basically modifications of this. So here's our indenter, and I'll just show you a movie. This is the electron microscope. Here is aluminum. This is effectively a single crystal because the grains are much larger than the field of view here. So here we have a single crystal of aluminum. Here we have our indenter, which looks a bit fuzzy because only the edge is not quite in focus. In fact, you'll see it starting to indent this material before you visually see the two come in contact. That's because part of the indenter is slightly out of focus in the electron microscope. So let me show you what happens. If I can get this movie to run. Yeah, it's running. Initially nothing because we're just bringing the indenter toward the microscope. In some of these indentation experiments, you can actually see the indenters oops, did it stop? What happened here? Shoot. There we go. In some of these experiments, you can actually see the indenter drawn toward the material by van der Waals forces as it gets close enough. That's not really visible here. All right, these little dark bands you see are just elastic contours. Did it stop again? Shoot, what am I doing wrong? I won't try to point anymore. Going? Yeah. All right, there it is. It goes in. Almost nothing happens. You'll begin to see a couple of lines appear in the material. These are early dislocations. And then you get the indentation. And all up here, all through the material, you see lines. They're kind of fuzzy in this old movie, but we can do a better job now, but this was the original movie, so I thought I'd show it to you. Those are dislocations. Now, just taking a few frames from the movie, a little bit better focus. This is before. Here's the indentation coming in. This is after. There's the indentation pit, slightly different in shape than you see in the laboratory because this sample is very thin in this direction. But here you see dark lines emanating from that pit. These are the line defects or dislocations. And it is the motion of these defects that have actually allowed the surface indentation to happen. Now, how does that occur? That gets us into plastic deformation, which you've just been seeing, the making of an indentation pit, the twisting or pulling or stretching of a bar in some permanent way, is a permanent change in shape. Changes in shape always happen by a kind of deformation known as shear. We really have two kinds of deformation, as we'll see later. You can change the volume of the material, or you can change its shape. The mechanical deformations that change the shape of the material are known as shears. And essentially, the simplest example of shear is the deformation that you would get in a pack of cards. If you put them between your hands and move them forward, what starts out as a rectangle becomes a parallelogram because you get a tilting of these edges and a shape change by shear of the entire material. If this is a crystal and you look more closely, what you will discover actually happens when you shear a material is that there is sliding of planes of atoms over one another, something like this. They will create steps on the surface, but the steps are microscopic, usually rather hard to see. So you actually, if you just take the extrapolation of those, you see the rectangle becoming a parallelogram by means of these steps, and that's basically what's going on when a crystalline material deforms. That's even true when we do what is usually the most common test of mechanical properties. We just take a bar and we pull on it, and we pull on it until it begins to form and stretch. What happens in that case? Once again, you get the sliding of planes of atoms over one another. But recognize that if I slide two planes of atoms on a plane that is tilted with respect to the tensile axis here, that as a consequence of that sliding, the sample will actually get longer. So I can make a material, if I just pull on it, I can introduce plastic deformation that makes it longer by sliding planes of atoms over one another. And that's the slip process that we want to describe. Here you see something that's not all that different from what you can see in your lab samples if you look closely enough. If I take a polished surface, I should focus this in, but I can't do it here, and pull it in tension. Here are the different grains or individual crystallites of the material. And inside these grains, you see a whole bunch of slip lines angled to the tensile direction, which is indicated right over here. These slip lines are where planes of atoms have slid over one another. And the net effect of that sliding of planes of atoms is to elongate the crystal. So our dislocation behavior produces macroscopic slip steps on polished surfaces. If you later on you will do indentations on surfaces that are polished in the laboratory. And if you look around the periphery of the indentations, you'll see those slip steps. They're visible easily under low magnification. They have to do with things that are going on at the atomic level. So the visible steps are in fact formed by the motion of millions, thousands of millions of dislocations, but they produce things that you can actually see in a low power microscope. Now what's happening here? Interestingly, I told you last time, I think, that the dislocation theory, the theory of how this kind of deformation happens, was simultaneously discovered or published by 3 people back in 1937, the same year. 2 of those people knew one another vaguely, but were working independently. The third was not even known to the other 2. It's surprising how often it happens in science that when the time for discovery comes, it gets made, often by several people at the same time, and this is an example. In fact, the mathematical theory of dislocations, the picture of dislocations, goes all the way back to the 19th century and was the product of mathematicians rather than physicists or material scientists. A guy named Volterra was one of the early people to publish the properties of dislocations. And the Volterra dislocation, which interestingly was not picked up by engineers or physicists until almost 100 years after it was first published, showed the motion of a dislocation the following way. Suppose now our problem is to get 2 planes of atoms to slide over one another. The difficulty is that if you try to do that as some rigid process, you have to break billions of bonds simultaneously and then reestablish them. You can calculate the force required to do that. It's enormous. Not only that's not what would happen. If I just loaded the crystal up so that it spontaneously deformed, we can do that in the computer now from first principles. And you don't get sliding of planes. You get a much different kind of deformation happening. So not only is it difficult to do this is not even what would happen if you just pushed on a crystal. So what does happen? Suppose I create what's called an edge dislocation of the Volterra type. Let me take the crystal, let me make a cut along a plane, something like this. Let me now take the top of that crystal and compress it with respect to the bottom of the crystal by a vector B in that plane, so-called Burger's vector. Now let's suppose that this Burger's vector B is a vector of the crystal lattice, so that after I've made this deformation, this top of the crystal and the bottom of the crystal fit together perfectly in this plane. If I then glue it back together, over the surface of this plane, I will have no way of knowing the plane is there, because I've moved the atoms just enough that they're back in registry according to the crystal structure. So I glue this back together. In Volterra's case, he imagined an elastomer rather than a crystal, the same thing. If I can get perfect registry here on the surface, then the surface disappears. The only place I can see the fact that this thing has been done is right here at the edge of that slip region, at the periphery. There I've got too much material. I've crowded the material in together, and it's got to jam in and sit there. So when I finish this process, I will wind up with a linear defect, which is a line along the boundary of this region, and that's all that I have. I won't see the cut surface. I won't see the residue of this operation unless I go out here and look at this step on the surface. All I will see is the extra material that's gathered along that line. Now, if we do that, if we create this, let me go forward and show it to you before I come back. This is just what that would look like in a simple cubic crystal lattice. Suppose I make a cut right here, take the top, compress it with respect to the bottom by 1 atomic step, and then weld them together back on the side. Well, there's going to be a little bit of elastic distortion here, but basically, these atoms fit right back together again. The only net effect is an extra half plane of atoms which sits right here and which terminates on this dislocation line. Now you can calculate the elastic distortion of the lattice due to the presence of that called edge dislocation. And that elastic distortion is pretty much confined to the periphery of the dislocation. Once you get a few atomic steps away from the dislocation, there's really no way even to know it's there. That's how you create it. Here's what it is. Now let's go back and take a look at what happens if we now move that dislocation. Well, the dislocation is the boundary of a region that is separated by this vector B with respect to the material below it. As I move the dislocation, more and more material has separated by this vector B. If I push that dislocation along this plane until it comes all the way out of the material, the final situation looks like this. I've moved the whole top of the crystal over the whole bottom of the crystal on this plane by this Burger's vector B. That is, I have caused the slip of the top over the bottom, planar slip by the Burger's vector B. And I've done it 1 step at a time. Last time I used the analogy for you, which is quite accurate. If you try to move a rug, and you just try to pull on the rug to move it, the friction is, if it's a sizable rug, it's so big you just can't do that. But if you move the rug with a ripple, if you send a wave down the rug and pull it forward so that it's moving forward with that ripple, you can do that. In a practical sense, that's the way you do it. If you do a little experiment, try to move a rug all by yourself, you just send a wave and let the wave pull it along. You move it 1 step at a time. And that's what happens with this dislocation. It can be moved relatively easily because it does not slip the whole crystal over the bottom all at once. It does it 1 step at a time as the dislocation progresses through the crystal. Well, let's go back to this model of a simple cubic crystal. In fact, this is the most complicated model of a crystal I'm ever going to show you. Crystals in true crystal structures, face-centered, cubic, hexagonal, are a bit more complicated in their geometry because of the way the close-packed atoms are. We use a simple cubic crystal as an illustration. Years ago when people could read my handwriting, I didn't use slides. I drew pictures on a blackboard. I've never been a great artist. And my picture on the blackboard of a simple cubic crystal kind of looked like this, but wasn't quite as clean as this little picture is. I had a student who was a TA in E45 at that time, a Japanese student who was now the director of a very large institute in Japan. And he was a TA, and on the midterm exam, one of the questions I just said, I had to draw a picture of an edge dislocation of a simple cubic crystal. And the students drew something like this, like I had, and he got them all wrong. He insisted only this kind of picture in full three dimensions should get any credit. And it was, since he just, the interesting thing about an exam is if you knock off credit for every problem, it doesn't change the curve at all. It just lowers everybody's grade. It was, I was kind of embarrassed because people would bring this in and say, well, here's what you drew, and here's what I drew. Their drawing was generally better than mine, but I was going grading the exam. Anyway, this is what an edge dislocation would look like in a simple cubic crystal. Notice only the material immediately around the line is distorted. So the dislocation is a true linear defect. We can image the dislocations, as you saw in the transmission electron micrograph back in the movie. They come out looking like kind of fuzzy dark lines. Well, of course, you're not imaging the atoms along the dislocation. You're imaging the distortion around it. You're imaging the strain field. And the fact that you see it as a black line is just telling you that it is a pretty well-defined linear defect. And that's what a dislocation is. How do we define the dislocation? The dislocation is a method of producing a certain slip in the crystal. You can find the vector of that slip, the vector B, by which you're slipping the top over the bottom, in the following simple way, which is general. In fact, you can apply to an array of dislocations as well as to one. You do what's called a Burger circuit. Suppose I have a perfect crystal, and I have a simple cube, and I make a circuit in that crystal that closes on itself. Step 1, 2, 3 this way, 1, 2, 3 here, 1, 2, 3 here, 1, 2, 3 back. Circuit closes. Suppose there is a dislocation inside that circuit. Even if I can't see the dislocation, I can find its Burger's vector by making the same circuit. 1, 2, 3, 1, 2, 3, 1, 2. Now it doesn't close. And the Burger's vector, or the amount of slip that dislocation causes, is the vector that is required to close that circuit. By convention, I can put the arrow in either direction, but that's what's called the Burger's vector, and it defines the amount of slip that dislocation will carry. There are, in fact, two ways to understand dislocations, which are both of which are very useful. One way to understand the dislocation is to recall how we created it. We took a cut, we distorted, slipped part of the top of the crystal over the bottom. The dislocation is a line which separates the region over which this plane has slipped by the Burger's vector B from the region that has not slipped. And B is just the amount of the slip. So if you want, you can say, let me just take the region that has slipped. The boundary of that region is a line. That line is the boundary of this area, and that's the dislocation. So the dislocation is characterized by the area it bounds and the amount of slip that's happened. Another way to imagine a dislocation is, as I've just described it, is a linear defect, which is defined by its line direction and by Burger's vector, which is the strength of the slip. I'll show you in a minute why both of those can be kind of useful. First of all, let's take the linear defect, and let's consider how it moves. If I have an edge dislocation of the sort I've described, it is not that difficult to move it. That's why these dislocations can rather easily cause slip. We'll discuss how difficult at a later point in the course, but you can see it's not that hard. If the dislocation is right here, edge dislocation, all I've got to do to move it by one step is to break the bond, one bond per plane, the dislocation threads through, but to break the bond that is connecting this atom to this atom in the plane and establish that bond between this atom and this one behind. The net effect will be to move this dislocation one step forward. You see, it's only a very local reconfiguration that is required to move that dislocation. So the stress, the force I need to do that is not that high. And dislocations in most materials are fairly easy to move. That's why many materials, metals for example, are ductile and fairly easily deformed. There is, however, a caveat on that, which is produces why is the slip that we see so planar? Why do the lines seem so straight? There's a very good reason for that. If you look up here, the dislocation moving in its natural plane, which is the plane that contains both the dislocation line and the Burger's vector, the motion is conservative. In order to move this dislocation one step forward, all I have to do in this plane is break this bond and establish that one. So there's only a minor reconfiguration is required in order to get that done. But in that case, the dislocation is moving along this plane, which is called the slip plane or the glide plane of the dislocation. And this kind of motion is called glide. Suppose, as an alternative, we were to decide to move the dislocation out of the plane, move it into some other plane, cause deformation in some other direction. What would we have to do? One or two things would have to happen. Suppose you want to move the dislocation up. There's an atom here. To move the dislocation up, you've got to get rid of it. The way you get rid of it is if there are vacancies in the crystal, and the vacancies diffuse to the dislocation and congregate along the dislocation line, then that will get rid of these atoms, move them out into the crystal, and allow the dislocation to move upward. This is an upward climb, and it is a process that requires diffusion. You've got to bring vacancies, you've got to find vacancies, you've got to bring them over here, you've got to do this kind of deformation. Similarly, if you want to move the dislocation down, you've got a problem. To get the dislocation down one step, you've got to add atoms. The easy way for that to happen is for an atom to jump from here to here, leaving a vacancy behind. These two processes are called climb. One of them absorbs vacancies. Vacancies are destroyed. You don't know they're there once the dislocation is climbed up. The other creates vacancies, the dislocation climbing down. Both of these processes are difficult, and in fact, they become significant contributors to plastic deformation only at rather high temperature, whereas we shall see diffusion is relatively easy. So edge dislocations can move easily in their glide planes, but only with difficulty out of their glide plane. And you see that experimentally on the edge of your indentation pits of the E45 web. Because when you look at the slip steps on the edges of those dislocation pits, like the ones I showed you earlier, they're straight. They're straight, they're flat, they're atomically flat, almost. And that's because the dislocation will move preferentially in glide, because it can do that in a conservative way. In climb, it is much more difficult. Well, this is what's called an edge dislocation. They're very important, and that's their structure. There is a second kind of dislocation. In fact, most dislocations are what we call mixed dislocations. But there's a second extreme kind of dislocation, and that's called a screw dislocation. And I keep remembering to bring a picture of a parking garage. I never do. In a screw dislocation, suppose I take the same crystal, make the same cut.